Last time, we talked about Fisher projection. We talked about taking a molecule from the sawhorse projection to the Fisher projection. We learned how to find R and S in the sawhorse, how to find R and S in the Fisher projection. One more thing we need to talk about is the use of erythro and threo terminology. This is actually used whenever you have Fisher projection with two chirality centers. Important, you need the carbon chain to be in the vertical. So I have carbon, 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 carbon. In fact, the longest chain in a Fisher projection, it is always written, it is agreed that whenever you are drawing a Fisher projection, you will put the carbon chain in the vertical part of the Fisher projection. Now, the erythro terminology, it is used when you have two chiral centers and when you have the two same groups or the two analogous groups on the same side. Then you say, I have the erythro configuration. So this is an erythro and this is other erythro. Both of these are, in fact, enantiomers. The threo configuration, when you have the two same groups or the two groups that are analogous on opposite sides, that will be called the threo configuration. Now, regarding naming, we learned all the rules how to name alkanes. We will learn in chapters 4 and 8, starting next lecture, how to name alcohols and how to name alkyl halide. But what we learned in chapter 7, we learned how to find the absolute configuration of any chiral carbon. And it could be either R or S. So now, if we are naming a compound that has chiral centers, we need to indicate the absolute configuration. How do we do that? Well, for instance, we will learn how to name this compound. It is 3-amino-2-butanol. 3-amino-2-butanol. Well, we will learn in chapter 4 that you have to number from the end that is closer to the OH. So it is 1, 2, 3, 4. You have NH2, which is, as a substituent, it's called an amino. So the name is 3-amino-2-butanol. The 2-butanol is our parent chain. The part that we are interested in this particular chapter is introducing the chiral centers. At carbon number 2, I have a chiral center. At carbon number 3, I have a chiral center. Then I have to put between parentheses at 2, what kind of chiral center do I have? Do I have an R or an S? At 3, what kind of chiral center do I have? Is it an R or an S? So I find around this carbon, this is carbon number 2. What is priority number 1 around this carbon? That's 1. What is priority number 2? CH. Is it this carbon or this carbon? This carbon. So I'm going clockwise, therefore it is an R. So I need to write 2R. At carbon number 3, where is priority number 1? Nitrogen. And then I have this carbon to be second in priority, and that will be third in priority. I am also going clockwise. Therefore, the name of this compound is 2R, 3R. However, here, this carbon is the same. 1, 2, 3, I'm going clockwise, so it is 2R. Now, around this carbon, I have 1, 2, 3. I'm going clockwise, but hydrogen is towards me. Therefore, it is an S. I don't need to rotate the molecule as we agreed last time. So now we can name any chiral alkanes. For instance, I would like you to practice how to name this compound. This is a chiral alkane. You need to name it. We will go through the same procedure, or we need to use all the rules that we learned in alkanes. What is the first thing we need to do? Longest chain. The second thing, numbering. Third thing, finding the substituents and put them in alphabetical order. And there is our name. Now, the fifth that we need to do is to find the chirality. Where are our chiral centers? This carbon, is it chiral or not? Yes. And this carbon, is it chiral or not? Yes. Now, we need to know from where to number. Do we number from this carbon? That will be 1, 2, 3. Or from this carbon, 1, 2? 1, 2. Correct? So you must number 1, 2, 3, 4, 5, 6. It is a heptane. At carbon number 3, you have a chiral center, you need to find it. And at carbon number 4, you have a chiral center, you need to find it. So between parentheses, you put 3, and it's going to be either R or S, and 4, it's going to be either R or S. Now, you can have chirality centers in a ring. For instance, if we are looking at the bromochlorocyclopropane, please correct the name. It is 1-bromo-2-chloro. Please correct it. It is 1-bromo-2-chloro. So 1-chlorocyclopropane, you can have RR and SS. As you can see here, if you put a mirror image, this is going to be the mirror image of this compound. And again, the mirror image of R is S. The mirror image of R is S. So they are non-superimposable mirror images. Therefore, these two compounds are enantiomers. What about the cis-1-bromo-2-chlorocyclopropane? Well, again, if you put a mirror right here, that will tell us that this molecule is, in fact, the mirror image of this molecule. This has a configuration of R. Mirror image is S. This has a configuration of S. The mirror image is R. They are non-superimposable mirror images. Therefore, they are enantiomers. Now, if I take the cis and the trans, if I take the cis-1-bromo-2-chlorocyclopropane and the trans-1-bromo-2-chlorocyclopropane, they are not enantiomers. Therefore, they are diastereomers. They are stereoisomers that are not enantiomers. Therefore, we call them diastereomers. Now, earlier in this chapter, we said, if you have a molecule with one chiral center, the molecule must be chiral. But we said, if a molecule has more than one chiral center, it might be chiral or it might be achiral. Well, basically, you need to find whether the molecule has a plane of symmetry or a center of symmetry. If it has a plane of symmetry or a center of symmetry, then the molecule will be achiral. For instance, let's look at the 2,3-butane-diol and find out how many stereoisomers do we have in this molecule. Well, you have the 2R3R, and that is chiral. You have the 2S3S, and that is chiral. And you have the 2R3S, and that is achiral. Fisher projection. This is the 2R3R in the Fisher projection. This is a 2S3S in the Fisher projection. And this is a Fisher projection of 2R3S. This is achiral. These two, in fact, are enantiomers. Well, 2R3R, 2S3S, you have a mirror image. If you put a mirror right here, you will see that this one is a mirror image of the first one. They are non-superimposable mirror images, therefore they are enantiomers. We can see that also in the Fisher projection. However, the third one, which is this molecule, it is achiral. In fact, it is superimposable on its mirror image. Let's look at the mirror image. Here is a mirror image. If you rotate this 180 degrees and you put it on top of this one, you will get every atom to be superimposed on itself. Now, a molecule with more than one chiral center, but it is achiral, that molecule is called meso. So a meso compound, it is a compound, it is an achiral compound that has chiral centers, but the molecule is achiral, which means that the molecule has either a plane of symmetry or a center of symmetry. The same thing if you are looking at it in the Fisher projection. You have a plane of symmetry. In fact, this plane is dividing the top half and the bottom half, where the top half is symmetric to the bottom half with respect to this plane, which is cutting the CC in the middle. So you have a plane of symmetry. In the Fisher projection, usually you can draw, the plane of symmetry is right here. Well, you can only draw a line, and that is enough to see that you have a plane of symmetry. So that compound is a meso compound. I'd like to ask a question before answering yours. Okay, go ahead, ask your question.
So can we generalize and say that erythro configuration forms them meso compounds?
Well, first we said erythro. It can be the same or analogous. So what if I have OH and BR? So you cannot generalize. Second, What if you have more than one chiral center? And that was the question I wanted to ask. Okay. Before we go into the second slide, I would like to ask you the following question. My question, does this molecule rotate the plane of polarized light? Yes or no? How many of you think that this molecule rotates the plane of polarized light? I want to see hands. Okay, which means when I ask my second question, all of you should raise your hands, because it's a yes or no question. How many of you think that this molecule does not rotate the plane of polarized light? There are many people who did not answer. You see, that's the beauty of clicker. I will see the percentages. How many of you have answered? Okay. How many of you don't want to answer? Why not? That's a good answer. Okay. The molecule rotates the plane of polarized light if the molecule is chiral. The molecule does not rotate the plane of polarized light if it is? Now answer. So does... I'm sorry? Okay, I'm going to repeat what I said. A molecule rotates the plane of polarized light if it is chiral. The molecule does not rotate the plane of polarized light if it is achiral. What's your answer now? So you have chiral centers here. What is the key to answer that question? Does the molecule has a plane of symmetry or a center of symmetry? So how many of you think that this molecule has a center of symmetry? And that is the wrong answer. You said that this molecule, you think or you thought that this molecule has a center of symmetry because you found this, right? Isn't it? Okay, it is the wrong answer. Why? Because in a Fisher projection, you have the bonds to be towards you. The molecule is not planar. To have a center of symmetry, you need the second bond to be away. You can never, ever talk about the center of symmetry in a Fisher projection. Never. So you cannot find the center of symmetry in a Fisher projection. You can talk about a plane of symmetry in a Fisher projection. So this molecule does rotate the plane of polarized light. Why? Because it is chiral. The molecule is chiral. You do not have, you have more than one chiral center, and you do not have a plane of symmetry in this molecule. Okay, what about this molecule? Does this molecule rotate the plane of polarized light? No? Why not? Yes, why? It has what? Plane. You can only talk about plane of symmetry. And if it has a plane of symmetry, it means it is achiral. It means it does not rotate. Your argument is against your answer. Right? If the molecule has a plane of symmetry, it means it is achiral. It means it does not rotate the plane of polarized light. But you did give me an idea about a question in the exam. Okay. Here is your plane of symmetry. OH and hydrogen and the carbon are in the plane. Then the top half of the molecule is symmetrical to the bottom half of the molecule with respect to the plane that has the carbon, the OH, and the hydrogen. Hydrogen and OH and the carbon. This is OH, hydrogen, and here is my carbon. Okay. Now, we can also talk about a plane of symmetry in cyclic compounds. Now, this molecule is a meso compound. Why is it a meso compound? So this is a meso compound, right? This molecule is a meso compound. Why? It has a center of symmetry. It has another center of symmetry, but the molecule has a plane of symmetry. Where is the plane of symmetry? Right in the middle. Right in the middle, right here. This is a plane of symmetry. This compound is chiron. It does not have a plane of symmetry. It does not have a center of symmetry. So the cis, it has a plane of symmetry. The trans does not have a plane of symmetry. If you have more than one chiral center, how many stereoisomer can you form? The answer, if you have n chiral centers, the number of possible stereoisomers is 2 power n. Now, if one of the stereoisomers is a meso compound, then the number of stereoisomers is going to be less than 2 power n. In the 2,3-butanediol, you have 2 chiral centers. The maximum number of stereoisomers is how much? 4. But because one compound is a meso compound, what was the number of stereoisomers that we found? Can you please? YouTube. Okay. What is the number of stereoisomers? 3. Less than 4. Anytime you have a meso form, then the number of stereoisomers is going to be less than 2 power n. For instance, in this compound, you have 4 chiral centers. 1, 2, 3, 4. You do not have any plane of symmetry in this molecule. Therefore, you do not have any meso. The number of stereoisomers in this compound is 2 power 4, which will be 16. This is the structure of cholic acid. You have 11 chiral centers in this compound. So the number of stereoisomers is 2048. One of them is cholic acid, which is this one, and the other one is the enantiomer of cholic acid. So 2048 minus 2, that will be 2046. So you have 2046 stereoisomers that are diastereomers of cholic acid. You have cholic acid. And you have another one that is enantiomer. All the other stereoisomers, they are going to be diastereomers of cholic acid. You will not be getting a question in the exam where you need to list 2046 stereoisomers of cholic acid. Okay. Now, what about having a double bond? What is the number of stereoisomers that you can have if you have a chiral center and you have a double bond? Well, the same thing about the stereoisomerism in cyclic compounds when we said you can have cis and trans. It means that you have the 2 groups to be on the same side or on opposite side. In alkenes, we're going to talk about that in chapter 5. When you are having an alkene, if you have the 2 groups on the same side, that will be cis. If they are on opposite side, that will be trans. Now, if these 2 groups are the same or analogous, you will, on the same side, you will name it a cis stereoisomer. If they are on opposite side, it will be the trans stereoisomer. But sometimes you have groups that are not analogous, and you cannot refer to that stereoisomer as cis. You use another terminology. It is called the Z. But Z stereoisomer is similar to cis stereoisomer in the sense you have the 2 groups that are of high priority on the same side. The trans or the E stereoisomer in alkene, you have the 2 highest priority groups on opposite sides. Fortunately, ranking the groups is exactly the same like ranking the groups about absolute configuration. So we will use the atomic numbers. We're going to go over that in chapter 5. But the fact that a chiral center can be either S or R, a double bond can be either Z or E, cis or trans, That means you can incorporate the double bond in this N. So if you have a double bond and one chiral center, the maximum number of stereoisomers that you can have is 4. Because the double bond can be either cis or trans, Z or E, and the chiral center can be S or R. For instance, if you are looking at 3-pentene 2-ol, you can have the ER or the ES, you have the ZR or the ZS. Reactions that produce diastereomers. In chapter 6 of Chemistry 211, we're going to learn a lot of reactions. And we are going to understand the mechanism and mechanisms of all of these reactions. But stereochemistry is very important in all of these reactions. So we're going to introduce these reactions during this chapter, and we're going to talk about their mechanism in the corresponding chapters in chapter 6 and other chapters as well. We're going to learn that if you have a C double bond C and you reacted with EY, E stands for what's called an electrophile and Y for a nucleophile. And basically what we will learn that you will put the E on one carbon and the Y on the other carbon. Now it depends whether you are starting with an alkene that is cis or trans, Z or E, what kind of stereoisomers you are going to get in the product. Because you have a carbon that could be a chiral carbon and a carbon that could be a chiral carbon if you have these two groups to be different. And it also, the outcome of this reaction also depends on the stereochemistry of the reaction. I have this EY. EY, they can be different or they can be the same. How do you get this molecule to approach the double bond? Do you get this molecule to approach from the same side? Or do you have the approach from opposite sides? So it depends on the mechanism of the reaction that the outcome of the reaction will be one stereoisomer versus another stereoisomer. For instance, we're going to learn about bromination of alkenes. We will learn the mechanism of this reaction. You add the bromine to a C double bond C. We will learn that one bromine is going to approach the double bond from one end and the other bromine from the opposite end. We call this addition an anti-addition. Now, if you are starting from a trans, you will get the bromine to add either from this side, which means that the second bromine is going to add from the opposite side. That will be this stereoisomer. Or you will get the bromine to add from this side or from this side. In fact, this is a meso compound. Whether you add from here and then you will get the second bromine here, or you add from here and you get the second bromine right here, that is a meso compound. Now, why is this molecule meso? It has what? It has a center of symmetry right here. Bromine, bromine, hydrogen, hydrogen, methyl, methyl. So you can see a center of symmetry. That's why this molecule is meso. So the anti-addition to the trans alkene is giving us a meso compound. However, if you add bromine to the cis alkene, you can add from this side, and then the second bromine is going to be from this side, or you can add from this side, and the other bromine is going to add from this side, which means you are going to get RR and SS, the enantiomer. But you can have 50% the bromine to add from this side, and therefore the other bromine is adding from this side, or 50% for the other enantiomer. That's why you will get racemic mixture. So in whether you are having a trans 2-butene or cis 2-butene, what do you know about the optical activity of your product? In both cases, you are going to have optically inactive. Why? Because one is giving you meso, which means that the molecule itself is optically inactive, and the cis is giving you a racemic mixture, which means it is optically inactive. We will also learn a reaction which is the epoxidation reaction. If you have a C double bond C and you add the peroxy acid, you will get an epoxide. If you are having the trans, you can add the epoxide, you can add the peroxy either from this side or from this side. 50% chance. You will get a racemic mixture. However, if you are having the cis, you are going to have a meso compound. What is the plane of symmetry in this molecule? It's exactly like that. The oxygen is in the plane, and it is cutting the CC in halves. So basically, we will refer to such reactions where the addition of the two groups are from the same side or from from opposite sides. We refer to this reaction as stereospecific reaction. It is called a stereospecific reaction. A syn addition or an anti-addition are examples of stereospecific reaction. They are specific to one stereo side of the reacting part of the molecule. In this case, it is a C double bond C. Each one of our stereoisomers that we started with, the alkene, whether I have the cis or the trans, is giving me a different stereoisomer. One of them is giving me a meso compound, the other one is giving me a racemic mixture. So the bromination reaction and the epoxidation reactions, they are examples of stereospecific reactions. In the bromination, you have an anti-addition. In the epoxidation, you have a syn addition. We will also learn in Chemistry 211 hydrogenation reaction, the reduction of a C double bond C into a C single bond C. We will see, after we understand the mechanism of this reaction, that when I take this alkene and I add hydrogen and platinum, I will get two stereoisomers. I am getting the cis and the trans, but I am getting one stereoisomer to be in excess of the other. We will understand why after we go over the mechanism. So the reaction is selecting one stereoisomer to be in excess of the other. The reaction is called stereoselective. It is selecting one stereoisomer to be in excess of the other. When you are looking at this C double bond C, you have the two faces to be prochiral. They are, in fact, diastereotopic faces. Why do we call them diastereotopic faces? Because one of them is getting me a diastereomer, the second one, the second diastereomer. Now, at the beginning of this chapter, I told you it is a very hard task to separate enantiomers. And it is very laborious work. And I also gave you an example about medicinal chemistry. If you are synthesizing a compound or you are isolating a compound, and you are having a mixture of enantiomers, and one enantiomer has the activity that you are looking for while the second enantiomer is lethal, then it is a must that you separate the two enantiomers. Now, how do you do that? We know that you cannot separate enantiomers by applying the common separation techniques in the lab, which you will learn in your organic lab, which are basically column chromatography, thin layer chromatography, recrystallization, distillation, and so forth. So what do? Well, you have a mixture of enantiomers. Let's say that this compound, we are symbolizing it with the C. I have a mixture of enantiomers regardless of the percentage, whether I have 50-50 or 99-1. One enantiomer will be rotating in the positive direction and the second one in the negative direction. That's why I am saying I have C plus, C minus. So a mixture of enantiomers. Then what do? You add another chiral center or another chiral molecule. But the chiral molecule that you are adding must be complexing to the C plus and C minus, so that when you are adding it, now you don't have enantiomers anymore. Now you have a mixture of diastereomers. So you have a mixture in your reaction mixture. You have a C plus and C minus. You added another material that is optically active. Now that optically active molecule is complexing with both the C plus and the C minus. So in the reaction mixture right now, you have C plus, P plus, and C minus, P plus. So you have a mixture of diastereomers. The stereomers, they have different properties, different physical properties. Excuse me. Then you can separate them. So you separate the two diastereomers. But then what you need to do is to decomplex the C plus P plus and the C minus P plus. You can anticipate the hard work to find the appropriate P plus that is able to complex with both C plus and C minus. Second, you need that P plus after binding to C plus and C minus to be able to debind it, to break it. Because your interest is in the separation of enantiomers, not in binding another molecule and leave it as it is complex. So that could be laborious, and it might take a long time to take care of it. One more thing to talk about stereochemistry regarding polymers. We will learn about polymers later about polymers in Chemistry 211. Basically, if you have a unit, we call it a monomer. If the same unit is binded to another unit, we call it a dimer. If you have 3 units, that will be a trimer. If you have 4 units, that will be tetramer. If you have many units, then it will be called polymer. Okay? Now, if you have a small polymer, you call it oligomer. An oligomer is a small polymer, so you have like 10, 15, 20 repeating units. Now, regarding the stereoregular polymers, you have 3 different types of polymers. You have the atactic, the isotactic, and the syndiotactic stereoregular polymers. If we are talking about polypropylene, the polymer polypropylene, which means the unit is propene, we will learn how to polymerize propene later in Chemistry 211. The atactic polypropylene, you have this chain right here, and you have the methyl groups to be hanging out of the methyl, out of the chain. But they are hanging out in a random fashion. So that is called an atactic polypropylene. The stereochemistry of the methyl groups is random. In fact, the properties of an atactic polypropylene are not very useful, particularly for applications like fibers. And the mechanism that we will be talking about in the formation of atactic polypropylene is the free radical polymerization. Another stereoregular polymer, which is very useful, that is called the isotactic polypropylene. In the isotactic polypropylene, you have all methyl groups to be hanging on the same side of the chain. Now, this is formed under a condition that is called the Ziegler-Natta conditions. In fact, Ziegler and Natta, they received Nobel Prize for their work on polymers. The other stereoregular polymer is the syndiotactic polypropylene. The stereoregularity here, you have the methyl groups to be alternating side up, side up, side up. That has also very useful properties, and it is prepared by the same method, which is the Ziegler-Natta conditions, which involves coordination polymerization. We are going to talk about such polymerization also in Chemistry 211. What concerns us at this stage in Chapter 7 is to know the difference between an atactic, isotactic, and syndiotactic polymers. The last section of this chapter. We have talked about stereochemistry, we talked about carbon. Does that mean it's only carbon that can exist as a chiral center? And the answer is no. For instance, silicon is also in group 4. You can have, if you are having 4 different groups around silicon, then you will be able to isolate a chiral compound. And in literature, many chiral compounds have been isolated involving silicon. What about nitrogen? Nitrogen in amines. Well, in nitrogen, if you are putting 3 different groups here and you have a lone pair, well, theoretically, you can have chiral amine if you have 3 different groups. But in reality, at room temperature, that is going to be very hard, Because what happens is that you are having this equilibrium or the pyramid to be inverted into the other pyramidal geometry to be happening so fast that whatever you are recording at any point is an average configuration of both. Okay? Now, of course, you can do something about that. You can slow the equilibrium. Can anybody tell me, how do you think? Decrease the temperature, exactly. So one way to isolate an amine in one chiral versus another chiral configuration is to lower the temperature. The phosphines, the phosphorus in phosphine, this equilibrium now is very slow. And in fact, chiral phosphines have been isolated. And the last example about chiral compounds, it involves sulfoxides. The sulfur in sulfoxides, you have this equilibrium to be very slow, and chiral sulfoxides have been isolated. They have been resolved. One of them will be rotating in the positive direction. The second one will be rotating in the negative direction. Now, at this stage, I am telling you what are the assigned problems in Chapter 7. But after we cover up to Chapter 6, then you go back to Chapter 7, and you will be able to solve all problems in Chapter 7. The only reason I am telling you what are the problems here in Chapter 7, it is because we have some mechanisms and some reactions that are covered in previous chapters, but we did not cover them yet. But we will do that starting, in fact, next lecture. This will be the end of Chapter 7. I'm not going to start a new chapter today. We will be starting the combined chapters 4 and 8 next lecture.